Hello everyone, today we'll talk about the problem sort an array. We're given an integer array, we have to sort it in n log n time with as good a space complexity as possible without using any built-in functions. So in essence we have to implement a sorting algorithm. There are of course many sorting algorithms, so it's our decision which we want to implement. In general, I think that you should know three sorting algorithms. The big two that in general everybody expects everybody to at least have heard about are quicksort and merge sort. And I would also add heap sort to that list. And if you were to be forced to solve this problem, I would choose to implement heap sort. But I'll talk about it later. Here I have some implementation of quicksort, because quicksort is one of the most popular sorting algorithms. It has some difficulties, some pitfalls, and also this version isn't even guaranteed n log n, and it's not that easy to guarantee n log n in pessimistic case for quicksort. Yet, of course, it has some benefits, because quicksort, for instance, can be used because of its natural algorithmic idea of partitioning the array. It can also be used as, well, a partition method. So it also means that it's a partial sort method, a selection method. The quick select algorithm for linear time finding of the kth largest or smallest element is essentially the same thing as quicksort. So it's important to know it. But I think it has too many caveats, too many decisions that you have to make sure that this whole algorithm actually ends up doing what it's supposed to and not, for instance, going into an infinite loop. That is not, I think, a good choice to implement it as your algorithm of choice. But it's good to implement it at least once. And I've chosen quicksort over merge sort, but merge sort still has some problems. In particular, most sorting algorithms will operate in linear space complexity, especially, for instance, heap sort, that in essence can sort an array in place without using any auxiliary memory. The same thing, of course, is true for our quicksort. But for merge sort, to make sure that the memory is linear is not that trivial, because, of course, merge sort makes it so that it splits the array into parts, sorts those parts recursively, and then merges the result into one sorted array. So you have two slices of the array, let's say two neighboring slices, that you want to merge into one sorted array. And it's not trivial to see, so let's say that this left and right part are sorted, but you have to make this whole thing sorted, which is a pretty weird face. And it's not trivial how to actually do it. And of course, how to actually do it without making many auxiliary arrays. So memory is a bit of a problem in terms of merge sort. But of course, merge sort has some advantages. Maybe it's more natural for you to think about it. And also in some problems, you will essentially perform merge sort. You will perform divide and conquer on an array. And in that case, it's good to know how to implement it, because it's not like you can just take a normal implementation of merge sort and modify it easily to, let's say, count the number of inversions in a permutation, which is a classic case where you would essentially implement merge sort to calculate something about the array. So let's jump into the quicksort, and then we'll also talk a little bit about heap sort. So the general idea of quicksort is very simple. You will sort the array in parts. You will start with the whole array, then separate that into two smaller subarrays and so on. And you will do that recursively. At the end, you'll have arrays that are empty or have a single element. You know that those arrays are sorted by definition. And then you'll combine those two sorted arrays, but not like merge sort, that you will have to merge two sorted arrays, but instead you'll have a guarantee that if those two subarrays are sorted, you don't have to do anything else to make sure that the larger array is sorted as well. So how do we guarantee that when we split an array into two parts and sort those two parts, then the whole array is sorted? Well, we can guarantee that if we know that every element in the left part is less than or equal to every element on the right part. Because in that case, we have essentially first separated our array into, let's say, small elements and big elements, in quotes. And then we sorted the small ones, sorted the big ones, and we don't have to do anything else. This typically acts by choosing a pivot element, which is the element that will be the middle element. We'll be separating elements into those that are less than it and those that are greater than it. And there are many ways of implementing partitioning, and most partitioning implementations have difficulties. They have difficulties with repeated elements. In particular, they can become quadratic when there are many, many repeated elements. Or they have issues that it's not trivial to ensure that we always reduce the array. So that if we select the pivot, for instance, we don't have a good luck, and we select a pivot in such a way that everything is less than or equal to that pivot, or greater than or equal to that pivot. In that case, we might then try to recurse on something that's, let's say, empty and something that's the original array, and in that case we are looping. So we often have to make sure that what we recurse over is smaller than what we started with. That at least one, and of course in order to do so, we must make sure after the partitioning that at least one element is in its proper place, and we have to recognize it. So this is the problem with partitioning. And one way to solve both of those problems, to solve the fact that repeated elements give us quadratic time, and to solve the problem of what to do with the pivot, we can use the Dutch national flag problem, the problem of sorting an array that has only 3 possible values, which is to just separate the array into 3 parts. Those smaller than the middle value, and those larger than the middle value. The implementation would go something like this. We'll remember the first element that's not smaller than this value, and the last element that's not larger than this value. And in that case, and of course this equal will be just going through all the elements, and it will kind of represent the elements that are equal to our pivot. And at the end, when we have this less and more calculated, we can recurse on less minus 1 and more plus 1. So now we make sure that everything between those 2 pointers are all the things that are equal to the pivot. It's of course also another problem on LeetCode to actually solve this Dutch national flag sorting problem. Because of course if there are only 3 different values, then just running this partitioning scheme will sort the array. But we'll go through all the elements that are not greater than our pivot, and we'll compare them. The element that we're pointing at is either smaller than the pivot, or it's equal to the pivot, or it's greater than the pivot, and you have to push the appropriate pointers forward, or in case of the last pointer backward, and swap when necessary. This is quite intuitive. There are no edge cases here, and at the end we don't have to worry about doing anything else, about going out of bounds, about making sure that the subarrays are smaller. So I think this is, or at least for me, it would be the preferable way of implementing partition. At the end, of course, we have to recurse on the whole array and return the sorted array. If we do it like this, then this is actually n squared, because in some pessimistic cases, quicksort is just n squared. There are ways to make sure that it is n log n. There is, for instance, the median of medians method of selecting a pivot that guarantees that we will actually have meaningfully smaller subarrays that we recurse into. One way that I don't see talked about that often is just to shuffle the numbers at the beginning. In which case, still it's possible to, for instance, shuffle the numbers and get a sorted array at the end and our quicksort to go quadratic, but it's very unlikely. So that's probably the easiest way to solve the n squared problem, though it is of course a built-in function which is not good for this problem. So if you want to fix the quicksort, then you can do so on your own. If you were to implement merge sort or heap sort, you wouldn't have to worry about that. They will go n log n because of their construction more naturally than quicksort, which is kind of wonky. And finally, a few words about heap sort, since both quicksort and merge sort, I'd say, are algorithmic algorithms. They're algorithms that have an idea of a procedure, and they implement that procedure. And heap sort is more of a data structure based algorithm, because it says, if we have some structure that allows us to, in logarithmic time, insert elements and remove elements, and that elements that we remove is always the biggest element, then let's put all our elements into it in n log n time, remove all our elements from it in n log n time, and we have a sorted array. Voila. So this is the whole idea of the procedure. The complexity hides, of course, within the data structure. And in general, for a heap, as a reminder, you have 3 operations. You should be able to create a heap in linear time. You should be able to insert an element in logarithmic time and remove an element in logarithmic time. If you want a priority queue, you need all those operations. But here, we could either take a shortcut of not creating our heap in linear time. So if you're ambushed with a problem like this to implement a sorting algorithm, and you don't remember how to create a heap in linear time, then don't worry, implement pushing elements upwards, downwards, and then implement this naive idea of adding all the elements, because when you add elements, you typically have to push them upward, and removing elements, then you have to push them downward, and so implement those two methods, and you will get a solution because both parts will work in n log n time. And if you only want to implement a single operation of pushing up, down, you don't want to implement both of them, so you only need to implement one, then of course you can use this standard linear time heap creation algorithm, and then you create the heap based on the nums array in linear time, and then you remove all the elements in n log n time, and you have a sorted array. And you can do it in place, because you can simply, since when you remove an element, you remove the root, you need a new root, so you can take, let's say, the last leaf and put it as root, and then you can put that root as the last leaf, and now remember that it's no longer part of the tree, so you can very easily sort the array in place. You don't have to think about anything else, you just swap the root with the last element, fix the heap. Swap the root with the last element, fix the heap, and it's very simple in that way. So if you're unfamiliar with heap sort, now is a good idea to remember it and then to have it in your toolbox for this sort an array kind of question.